Hello everyone, I hope you're all doing well. We're going to be looking at moments about an axis today, and I'll be handling this by means of a conceptual problem. Okay, so moments about an axis or line. Okay, they mean the same thing. Okay, and like we have done in the past, we're going to have the scalar approach and the vector approach for this. So let me first look at it from the point of view of the scalar approach. Okay, so scalar approach. And like we have done for typical moments about a point, in the scalar approach, this idea is the same. You have to find a perpendicular distance and then use the right hand rule. Okay, so let me consider some kind of a general problem here. I'm going to draw that up in a minute. Okay, so here is the z-axis for me, and then here is the x-axis for me, and then here is the y-axis. I need to get it as a straight line. Of course, always my downfall, right? Okay, and then I indicate it as a y-axis here. So this is x-axis, this is the y-axis, and then this is the z-axis. I'm going to take the x-axis and extend it onto the other side as well, okay, if you don't mind. So let me extend this onto the other side so that, and then I'll draw this as a dotted line. And what I'm going to say is there is some kind of an object, a rigid body, which is lying on the xy plane. Okay, so the rigid body, I'm going to draw it in the following manner. Okay, so this is going to be having a certain length along the y-axis, and then it's going to have a certain length along the z-axis. And you'll see, let me draw this as a slightly deeper font size here. Okay, all right, so this is the rigid body. So let me call this as the point O, which is the origin, and then let me call this as the point A. Okay, and then I'm saying that on this rigid body, which is lying on the xy plane, as you can see, there is a force that is acting. Okay, this force is acting, and it's directed vertically up. Okay, so there is a force that is vertically up, and this is the force F. Okay, so let me say the magnitude of this force is F. And then let me also say that the distance from point O to point A along the y-axis is given to me. Okay, so let me draw that distance out here. Okay, let me make sure this is parallel to the x-axis. And this distance here, which I'm going to mark in a second, is d suffix y. Okay, so I'm going to call this distance as d suffix y, because this is a distance along the y-axis. And likewise, I also have a distance along the x-axis, which I'm going to write out in a minute. Okay, so that's this distance here. So I draw a line parallel to the x-axis. I need to take this creature and then move him a little above here. Okay, so that's the point A. And then, I join these two by a nice smooth line here. And that distance, I'm going to say, is d suffix x. Okay, and let me draw these dimensions in terms of dotted lines, as you know by now, right? That's typically how I do it. Okay, and one more here. Okay, and this last creature. Excuse me. Okay, so I have this figure down here. Okay, so the body is on the xy plane, which is this bar OA. Okay, so let's say that these are the following things. So there's a solid bar, OA, which is L-shaped. Okay, this is on xy plane. Okay, and then there is a force. The force is F. It's acting parallel to the z-axis. Okay, so what do we need to find? Okay, so obtain the moment of the force F about the x-axis and the y-axis. Okay, so the idea is we need to obtain the moment of this force, okay, about the x-axis and the y-axis. And essentially that's the topic of this talk here, right? We need to find moments of this force about a line or an axis, and I'm going to be using the scalar approach. Scalar approach is fairly easy, okay? So here is the basic idea. If I'm using the scalar approach, here is what you do. The magnitude of the moment, about a line or axis of interest, okay, is given by multiplying by the product of the force and the perpendicular distance from the line of interest, the line or axis of interest, to the line of action of the force. Okay, so this is typically the scalar approach. Okay, let me underline some keywords right down here. So if you're using the scalar approach, okay, the magnitude of the moment about a line or an axis of interest. Okay, well, I wanted that to be a straight line. This is sometimes frustrating, especially early in the mornings, okay, is given by the product of the force, okay, and the perpendicular distance from where? From the line or the axis of interest all the way to the line of action of the force. Okay, so that's typically the magnitude. This is exactly what you have done when you did moments about an axis, so there is not much of a difference here. Okay, and the direction is going to be given by the following. The direction is of course going to be given by the right hand rule. Okay, so the direction, well, I missed out on my pencil. So direction of the moment is given by the right hand rule. And what is the right hand rule here typically? So here is what we do. So align the right hand fingers along the line of action of the force well, okay, the second step is your palm should face the line or axis of interest. And then the third step is curl your fingers okay, and the direction of the thumb is the direction of the moment. Is the direction of the moment, and the curl of your fingers is the sense of the moment. Okay, so once again, we are making use of the right hand rule in order to obtain the direction of the moment. Okay, so align the fingers of your right hand. Okay, and this should be along the line of action of the force. The most important thing here is your palm should be facing the line or the axis of interest. Okay, and then what you'll do, you'll curl your fingers. The direction of the thumb will give you the direction of the moment. The curl of the fingers will give you the sense of the moment. So this can be either clockwise or this can be counterclockwise. Okay, and I'm going to use this for the problem that I've just drawn above. Okay, so making use of the magnitude and the direction, how do we find the moments? Okay, so let me go back and take a look at the problem that we have. Okay, so I'm going to take this creature and then bring it down to the next page. Okay, all right, so now let me say moment. So this is by making use of the scalar approach. Okay, so moment about the x-axis due to the force F. Okay, if I'm looking only at the magnitude, okay, moment about the x-axis due to the force F, the magnitude of this moment is going to be the magnitude of the force F times the perpendicular distance from the axis of interest to the line of action of the force. Look at this. What is that perpendicular distance? So I can do the following, right? I can say, okay, let me take this color here. So all the way from the x-axis, which is the axis of interest, to the line of action of the force. That is going to be the perpendicular distance for me. And that is the same as the distance d suffix y as I have marked, right? Which means that this is going to be F times d suffix y. Okay, so this is the magnitude of the moment. What is the direction of the moment? Okay, so this is the magnitude. I guess let me write this as 1, and then the direction. Okay, right hand rule. How do you do the right hand rule here? You take the fingers of your right hand, align it to the direction of the force. So your fingers will be pointing up. Then your palm should be facing the point O. Curl your fingers. It will look as if you're clutching the x-axis with your thumb pointing along the positive x. And that's the direction of the moment. Okay, so if I draw it out here, it's going to be pointed this way. Okay, so this is going to be the direction of mx due to the force F, and so this is in the I direction, which means that if I go back here and write it out, then so by using the right hand rule, this is going to be in the x-axis direction. Okay, by using the right hand rule. Okay, and then so I can now write the moment as a vector. Mx due to the force F is going to be F times d suffix y in the I direction. Okay, so this is the moment as a Cartesian vector, Cartesian form. Okay, and we're going to do the same thing for the y-axis. Okay, so moment about the y-axis. Moment about the y-axis due to force F. Once again, the magnitude. Okay, so my due to the force F, I'm looking at the magnitude of this. This is going to be force times the perpendicular distance. So if I go back here, what is the perpendicular distance? From the axis of interest all the way to the line of action of the force. Okay, so which means that I can typically do it this way. Look at this. So let me choose a different color, and let's say, okay, so I'm good here. So first thing is, okay, where is the axis of interest? It's the y-axis, right? So from the y-axis, I draw a line that is parallel to the line of action of the force. Look at this. Okay, so let me make sure that this line is parallel to the line of action of the force. Then I take the line of action of the force and I extend it a little bit. Okay, so I should go back to my color here. I take the line of action of the force and then I extend it a little bit. And you can immediately see that, okay, the distance between these two is going to be this distance here. Okay, so that's going to be d suffix x, as you would have guessed it. and so this is a perpendicular distance, and so this is d suffix x, which means the moment is f times d suffix x, and this is a moment about the y-axis. Okay, so this is going to be f times d suffix x. Okay, so this is the perpendicular distance here. Okay, or let me write it in the same way that I had written the previous one. So this is f times multiplied by d suffix x, and then the direction, once again you use the right hand rule, and obviously in this problem, because it's a first problem that we're doing, it's going to be kind of straightforward, but you'll see that for other problems we'll come up with an algorithmic way almost of solving these problems. Okay, if I use the right hand rule, here is what I do. Fingers of my right hand aligned with the force. My fingers are now pointing upwards, as yours should be. Then my palm is facing the axis of interest. Curl my fingers. The moment is going to be directed about the positive y. Okay, so essentially this is what I'm going to be getting. Okay, so this is the sense of the moment, and then that is the direction. So this is going to be my due to f. Okay, so the sense of the moment is as if a person who's sitting on the positive y-axis will see it as counterclockwise. Okay, so let's see if I draw a couple of creatures here. Okay, so if I look at it from here, okay, so according to that person, this moment will be counterclockwise, and the previous case, if I was sitting in the x-axis and if I was viewing this person, that will be coming across as counterclockwise as well. Okay, so the direction of the moment is about the positive x-axis. Okay, so this is about a positive y-axis in this case. Okay, and so my due to f is going to be f times dx in the j direction. Okay, and this is the Cartesian form. And if you want, the sense of this moment here, let me write a statement, is counterclockwise as seen by a person from the positive x-axis side. Okay, that is this person which I'm putting a tick mark against. Okay, and then I can look at the next one, okay, which is this guy here. So this sense is also counterclockwise as seen by a person from the positive y-axis side. Okay, and that is essentially, if I go back and look at this person here. Okay, so this is essentially the scalar approach. It's fairly straightforward. Just do force times perpendicular distance, you get the moment. What is the direction? The right hand rule. Combine everything together, write it as a vector. Okay, so these are the two things that we were supposed to do. Moments about the x-axis due to the force F. Okay, and then I also have moments about the y-axis due to the force F. Okay, now let me go to the vector approach. Okay, so here is my outline for the vector approach. So let me say this is, I guess I call the scalar approach as 1 probably, or A. Let me call this as B. Okay, so vector approach. Okay, in the vector approach, I take the following steps. Okay, first step, let me go back to my regular color. Okay, and I typically always forget that you don't need to, tap on the screen to go back to the way to write things. Okay, bear with me while I get used to these things. I never get used to these things, I tell you honestly. Okay, first step. So steps to take. Up. There we go again. Okay, so steps to take. First step, express the force as a Cartesian vector. Okay, and what I'm going to do is I'm going to take my figure from above. Okay, so not this one, but the cleaner one, which was here. I'm going to copy this figure, and I'm going to bring it down here. Okay, so that we can take a look at this figure as we are writing out these steps. It is very obvious to see that if I write this force as a Cartesian vector, it's going to be having a component only in the z direction. Okay, so this is going to be the force F is 0I, 0J, and then F times K. Okay, this is the first step. Okay, then the second step is this. Okay, choose any point on the line or axis of interest. Okay, and what am I doing here? So let me say that I'm trying to find moments about the x-axis. Okay, in that situation, I could choose a point O on the x-axis. So let me write that out. So for this step, so say we want moment about the x-axis, which means I can choose point O, which is a point on the x-axis. Okay, once again, the key word is I can choose any point in the line or axis of interest. Okay, so in this case, I choose the point O. Then I write the coordinates of that point O. Okay, so I choose the point O, which is 0, 0, and 0. And then my third step is the following. Okay, so I'm going to scoot up a little. So my third step, from the point of interest, chosen, okay, obtain the moment of the force about that point. Obtain the moment of the force about the chosen point. Okay, or let me say, yeah, so the point of interest that is chosen is point O, and in this case, if I want to find the moment of the force about the point O, what do I do? So this is typically what I do. Okay, so then here I use cross product. Okay, if I do the cross product, then here is what I end up getting. First thing is I need to find the position vector, right? So what is the position vector? So I'm going to go from the point O all the way to the point A. So that's going to be my position vector if I am to find the moment about the point O due to this force F, right? So this is going to be ROA. Okay, so in this case, I'm going to have ROA as the following. So ROA is going to be coordinates of A minus O. So let me write the coordinates of A here. This is going to be minus dx, dy, and then 0. And so the coordinates of OA, the position vector OA is going to be minus dx in the I, dy in the j, 0 in the k. Okay, and then the force vector F was 0I, 0j, and then F times k, which means if I have to find the moment about the point O due to the force F, this is just going to be the position vector crossed with the force, right? This is typically what you've been doing for the scalar vector approaches. And this is the determinant I, j, k. Second row is going to be minus dx, dy, 0. Third row is going to be 0, 0, and then f. If I compute this determinant, I end up with the following. Okay, so this is going to be I times f d suffix y, and then I'll end up getting plus j times f d suffix x plus 0 times k times 0. Okay, so this is what I'll end up getting for this moment. Then my next step is the following. Okay, what you want to do is this. You want to go back to your scalar approach and say, okay, hey, what was the moment about the x-axis? When I use the scalar approach, the moment about the x-axis was f times dy. So in order to get only that guy, here is what I do. The magnitude of the moment about the axis of interest is given by the dot product of this moment that I have done with the unit vector along the x-axis. Okay, so here is what I have to do. So u suffix x is the unit vector along the axis of interest. Okay, so which means for us, if I'm doing it along the x-axis, then u suffix x is equal to I. If we are doing it along the x-axis, okay, or if we are doing it along the y-axis, if we were computing moment about the y-axis, then for me I would be writing as u suffix y, which is equal to j. Okay, so in this case it is just going to be u suffix x, dot product of two vectors, right, is going to be a scalar. So notice that this is the magnitude only. Okay, this is the of the moment about the axis of interest. Okay, this is just the magnitude of the moment about the axis of interest. This is not the entire thing itself. Okay, so which means if I do this, then here is what I end up getting. So mx due to the force F is going to be, look at this, so this is F times dy in the I, F times dx in the j, 0k dotted with I, which essentially just gives me F times dy. And the last time, to express the moment about the axis as a vector, I have to take the moment, the magnitude of the moment. Okay, let me write this properly. So magnitude of the moment, which I just calculated in the previous part, and multiply with the unit vector. Okay, this is typically what you've been doing to find the force as a vector. You know, I take the magnitude of the force and multiply it in terms of its unit vector. Okay, so this essentially is going to end up giving me F times dy in the I direction. And likewise, I can do the same thing for the y-axis. Okay, so likewise, to find moment about the y-axis, okay, choose a point on the y-axis, choose any point on the y-axis, and if I can choose the point O, okay, then I already have the vector written, the force as a vector. Okay, then I'll find the moment, find moment of the force F about the chosen point, okay, which I already have, which is MO due to the force F. And then here is what I do. Okay, so to find the magnitude of the moment about the axis of interest, I take the dot product of the moment I found out with the unit vector along the y-axis, which is going to be the following: F times dy I, F times dxj, 0k dotted with j. Okay, that's the unit vector, which means that the magnitude of this moment is just going to be F times dx. Okay, this is just the magnitude, notice that. Okay, this is not the x-axis, that's the y-axis. And then to find the moment as a vector, I take its magnitude, multiply it with the unit vector. which means that my about f as a vector is going to be f times dx in the j direction. Okay, I hope this makes sense to everybody. And these are the same answers, of course, as you got from the scalar approach. So very quick recap of what we have done, okay, in the vector approach. Okay, in the vector approach, the first thing is this: express the force F as a vector. Okay, that's the first thing. This is 0i, 0j, and 0k, fk, sorry, not 0k. Then I take, what is my problem? I need to find moments about the x-axis. So I choose a point on the axis of interest, or choose any point on the axis of interest. Look at this. That's something that I want to specify. You can choose any point on the axis of interest or the line of interest. Okay, it need not be a particular point. Okay, so I choose the point O on the axis of interest, and then at that point of interest, I obtain the moment of the force about the chosen point, and then I use the idea of cross products, which I have done here. And then if I want to find the moment about the particular axis or line of interest, then all I have to do is take the dot product of the moment with the unit vector along the axis of interest. Okay, so that's something I want to underline here too. So this is the unit vector along the axis of interest. Okay, and likewise, and if you want to write everything as a vector, then this is the Cartesian form, where I take the magnitude of the moment and multiply it with the unit vector. So this is the Cartesian form. And the same procedure is obtained for the y moment as well, about the y-axis. So vector approach, scalar approach, both of them are elegant, and depending on the problem, we will use one or the other, but it's good to know how to do both. All right, thank you very much. Stay safe, and I'll see you in the next problem. Bye bye.